Good morning. Good morning and welcome to the Transformational Technologies session. This session will deal with technologies that are soon to be deployed or recently deployed in the marketplace. The technologies will be presented and the possible impacts they might have on the industry discussed. I want to highlight the transformational nature of these technologies. They have the ability to significantly change the way in which pipeline integrity is managed. My name is Tom Bubenek. I'm a vice president at DNV USA. I'm responsible for the development, management, and implementation of projects related to all aspects of pipeline integrity management. We will have three speakers today from Saipem, Roland, and Petrobras. Please hold all questions until the end. However, you can add a question at any time in the chat function. We'll start off this morning with Christian Navoso. Christian is based in Salvador, Bahia, Brazil. Salvador is a capital of Brazil's northeastern state and is well known for its Portuguese colonial architecture, Afro-Brazilian culture, and tropical coastline. Christian is working for Saipem de Brazil. He has a master's degree in electronics engineering and has worked for Saipem since 2002. He has experience at SONSUB, which is a subsidiary of Saipem for special subsea equipment development. And during the past 3 years, he has been leading a specialized team in robotics based in Salvador for the deployment of the Flatfish autonomous utility vehicle, underwater vehicle, an advanced resident autonomous subsea vehicle. Christian will discuss the use of the subsea drone system to inspect or to perform complex inspections of subsea components and assets. The developments in the future are expected to include new capabilities for riser inspections, data harvesting from subsea sensors, and contactless monitoring of cathodic protection systems. Saipem team is coordinating with Sinai Cimatec for the development of the advanced functionalities to be embedded in the Flatfish technology. So with that, I'd like to welcome, please, Christian Navoso. Take it away.
Thank you. I'm going to share my presentation. Okay. Good morning, everybody. Thank you for being here today. We are going to present today a new advanced approach for autonomous pipeline inspection. That is the Flatfish AUV applied to subsea inspection of complex fields.
Good morning again. We're going to switch the order of our speakers a little bit, in that we'll start off this morning with Roland Palmer Jones. Roland is a group business line manager for integrity solutions at Roland, and he's responsible for the consultancy, testing, and software services that Roland delivers worldwide. He has spent 18 years in pipeline consulting. He has been with Penspen, and he spent 5 years in research and development at British Gas. Roland will discuss in his presentation and in this digital age how we are all getting used to the benefits of virtual reality to help us to be more efficient and to make better decisions. In his presentation, Roland will explore how we use virtual reality every day and how we might use virtual information to help us with pipeline integrity management and virtual pipeline inspections. Roland, I'll turn it over to you.
Hey, thanks, Tom. Sounds like you've been working for Pembina recently, if that's the name on your mind. Anyway, I will share my screen and we'll make a start. Thank you. Make sure we get the right one. Share.
Looks like it's coming
Okay,
up.
I hope you can all see that now.
Yes, I can.
Good. So are we showing display?
You're showing your screen. Yes.
Yeah. We have which screen are we sharing? No, I want to do.
Want to switch on?
Yeah. So you see, okay, good. You've got the proper view. Just
We're in
checking.
great shape now.
So, okay. I've got a question for you all. What is this? Hopefully you're all familiar with this type of picture. So it's a screenshot from Google Maps, and what I did was I pretended I was in Sao Paulo somewhere, and that I wanted to get to the beach, and I asked for a prediction on a journey. So this is a virtual journey to the beach. It's saying, okay, Roland, Google is saying, okay, Roland, if you did this journey, this is the route we recommend you take, and this is how long it would take. And here's an alternative. And you see it's around 1 hour 40, 1 hour 50 minutes. And I'm amazed for Sao Paulo, the traffic looks pretty good. No red stops or problems. So, but that was 7 a.m. in the morning, Sao Paulo time. So it's pretty quick. So what's this version? So some of you may know that if you're looking to plan a journey in Google, you can say, well, actually, I don't want to leave now. I want to leave sometime in the future. And so you can plan a journey later that day or later the week or next year or anytime, and it will make a prediction for you. So this was a different time. It's a virtual journey in the future. And the predicted time is not shown on the screen, but the predicted time at 5 p.m. on a Friday is more variable. They're saying it could be anything between 1.5 to 3 hours. And you can see that they're predicting some traffic hotspots. Again, a few little red spots on the screen here, which are where Google predicts that at a certain time on a Friday in Sao Paulo, there will be heavy traffic. You also see some heavy traffic down close to the beach. So 3 hours, do I still want to go at 5 p.m. on a Friday? Well, that doesn't sound too bad. If I'm going to go and spend the weekend lying on the beach, maybe it's okay. So it's helping me make that decision about whether to go to the beach for the weekend or not. Well, so the question is, how does this sort of thing work? How does Google make these predictions on journey time for their virtual journeys? Well, they have a lot of data. They obviously know about the road network, the types of roads and the speed limits. They have live public data from roadworks, road closures, traffic data from road sensors. They also use phone GPS data. They know where people are, traffic movement, live movement of phones, historic movement of phones as a substitute for traffic. And of course, they also get user feedback. People will provide information on accident locations, road closures, and so on. And more than likely, Google have some secret stuff that they don't tell us about in terms of how they analyze that. But what I experience, and I think many other people do, is that it can be very accurate. You can make a prediction of when you're going to get there, and usually it's pretty good. The future ones, there's more variability because you don't know the conditions at the time, but the live predictions are usually pretty good. Not always, though. So here's another prediction. This is a prediction for New Year's Eve. And amazingly, it looks like the road is totally clear on New Year's Eve to get to from central Sao Paulo to the beach. But I'm sure many of you will know that that's not really the case. Google predicts light traffic, but maybe they don't know about the New Year's Eve fireworks that will happen and how everybody from Sao Paulo will want to go to the beach to watch the fireworks, and everybody will get stuck in traffic probably for the whole day and night. So Google's predictions are good, but they're not always good. So here's an alternative. What's this? Well, this is a virtual inline inspection of a pipeline. And what we're predicting here is the severity of corrosion per pipe joint on this particular pipeline. And this pipeline is in pretty good condition. You can see most of it is green, and typically green means good. But there's one short section with a few pipe joints where the feature density is predicted to be more than one corrosion feature per square meter of pipe. So there's a higher density of corrosion. And again, it can be pretty accurate. Now, be aware these are log scale charts, so there is quite some scatter. But on some tests we've done on across a network, a large network of pipelines, we can get to this sort of accuracy where you can predict anomaly density reasonably confidently, obviously some spread, and predict maximum depths quite well as well. Although you'll see there is a tendency to over-predict maximum depth relative to true. But again, it's for an early stage technology, we think that's a pretty good performance. So we think it can be pretty accurate. And just to illustrate that, I'll take you back to the pipeline where we made the virtual prediction of condition and say, well, what was the reality? Well, you know, we actually had inline inspection data for this line, and what did we actually find? Well, it's not a perfect match to the prediction, but in the area where the prediction was for some joints in poor condition, we found that some of them are genuinely in poor condition. And we've done it slightly differently. It's categorized, but essentially if it's red, it means there's a high density of features, and some of those features may be deep. And if it's green, then it means the condition is pretty good. There's not too many features and they're not too deep. So essentially, we're highlighting the same segment and identifying that the rest of the pipeline should be in pretty good condition. And for the nerdy people who are interested in such things, it's a 10-inch diameter pipeline with a 7.8 mil wall thickness. It operates, design pressure is 50 bar. It's a low grade, grade B. It's a 1950s vintage, and it transports kerosene. So, we can see some of the issues there. You might ask, well, why do we think there's corrosion at this location? Why were we predicting? Well, there's a few things that might be pointers that you can even see on this picture. You can see there's a river here, so it's likely this is a low elevation point, and typically corrosion engineers will tell you that low elevation points can be wetter and have more wet cycles, and that can be an issue for corrosion. There's likely some topsoil variation as we go into this location, and also generally it's a fairly wet area, but that would affect all of the line, not just this little section. Interesting also, this section looks like it's some sort of diversion or some such from the original route, maybe. Not quite sure there, or a particular going around something. We don't know what was there in the 1950s when it was built. Just a question: what's the situation now? We're always interested to know what's happening on the ground. We can make a prediction. We can look at a map, but what's happening these days? Well, I was interested to see that when we zoomed in on some recent satellite photos, that actually there's a housing development going on around this corroded section of pipe. Thankfully, though, you can see the pipeline right away is nicely fenced off and protected from any damage due to the construction work. So that should be all right. So the same question that we had for Google: how does it work? Well, mainly with data and what we call predictor variables. And obviously there's some data around the pipeline, the type, the location, the construction year, the coating. There's public data available on soil types, rainfall, slopes, crossings, terrain. And of course, you can't make these predictions without some anomaly data, historic pipeline inspection data, maybe not for the specific pipeline you're looking at, but for other general pipelines. And of course, we have some secret stuff that we do in the background to bring it all together. But this model, as again a trial case, was developed using data from 755 pipelines, for over 3 million pipe joints, and a million external corrosion anomalies. So it's a reasonably large data set, but we do feel that we need to probably go to bigger data sets to get more accuracy and more awareness, because there's so many different corrosion types that can occur that to catch them all, the models need a lot of data to be able to pick that up. So what does that mean for the future? Well, Google Maps uses virtual journeys to help us plan when to make our real journey, what route to take, and even how to travel. You'll see you get choices if you drive, if you take a train or a bus, and so on, and it'll give you a lot of help. And that's very useful in day-to-day life. But what can virtual ILI, or this sort of virtual prediction of condition, help us with? Well, I think it can help us predict the condition of pipelines that we can't easily inspect. So we know that's a problem for the industry. We have lots of pipe segments that are very difficult to inspect. And we maybe need to make choices about which ones to make inspectable, what priority to do them in. And so this sort of technology may help us there. It can help us when to run real inline inspection. So again, you can look at lines that maybe you have inspected in the past, but a long time ago, and say, is it time to run again? What would we predict is going to be there? There's potential to help us decide what technology to use. That example I showed you focused on external corrosion, but it might be possible to extend it to other threat types. You may be able to look at what if scenarios. What if we change the coating? What if we do some repairs? What if we do something different? What if we replace that particular segment that was problematic? Are we going to improve the matter? And you could even think about almost like a constant monitoring. Once you can make a virtual prediction or have a virtual inspection, then there's no reason why you can't update that every hour. Obviously, it won't change very much most of the time, but you can pick up how live changes in CP or rainfall or traffic may make small changes. But I'll just leave you with one last thought. I've kept the presentation short, so leave some time for questions. But one last thought. What if we had a virtual ILI for external damage? If it was well set up, would it predict a higher probability of damage if there are roadworks and a build-up of traffic near a road crossing? So with that thought, I'm kind of bringing together the Google Maps thing, where Google will see that there are roadworks that are reported. It will show you where there's a build-up of traffic. If we integrated that with our virtual inspection, would we say, oh, okay, here's a location where there's a pipeline crossing the road, there's some roadwork, there's something going on, there's traffic there. Should we be worried about damage? Should we send somebody to site to check it out and make sure that our pipeline is okay? Or these days, send a drone maybe to site. So that's what I wanted to leave you with, the idea of virtual inspection, which is becoming a reality little by little, with some small examples, and I think offers a lot of potential for the future. And I'd be very interested to hear other people's suggestions and ideas. So with that, thank you very much. And I think we'll be doing questions now or at the end. I forget.
Yes, we'll hold questions until the end.
Okay.
Thank you for a very interesting presentation on the future and what we might expect as we look forward to virtual pipelines and virtual pipeline inspections. I'd like to move a little bit further along now, and I'm going to switch to Carlos. Carlos de Oliveira Cardosa is a subsea Brazil manager, Sonsub Brazil manager. He's a subsea pipeline engineer working with design and integrity of rigid submarine pipelines. His career has focused on high pressure, high temperature pipelines, pre-span fatigue due to vortex-induced vibration, things like pipe to soil interaction, foundational analysis, general finite element analysis, and development of specialized software during the last 21 years at Petrobras's Research and Development Center. Carlos will give us a brief overview of the digital twin theme as applied to subsea pipelines. A digital twin is or can be defined as an adaptive model of a complex physical system. Carlos will discuss the development of digital twin elements, and he will address the most relevant failure modes and technological limitations for our application to integrity management, to life extension, and to requalification. So I'll turn it over to you, Carlos. Would you please give us the next presentation?
Hi, good morning for everyone. My presentation will be in Portuguese, but at the end of the presentation, the questions can be done in English, okay? I will share the presentation now.
Okay.
Sorry. Stop showing. No,
Stop
sorry.
showing the presenter.
Okay.
Perfect.
Ok. Bom dia para todos, tá? Como eu disse, eu vou fazer a apresentação em português só para deixar um pouco mais dinâmica, tá? Ao final, nós podemos fazer os comentários e dúvidas em inglês, tá? Aqui a ideia, eu vou dar uma visão bem breve, né, sobre a parte de Digital Twin que nós estamos vislumbrando na Petrobras, tá? Nós estamos no início de um processo. O título da apresentação é uma breve visão, né, da tecnologia, né, de Digital Twin para dutos rígidos submarinos. Ok. Um breve sumário, né, do que nós vamos apresentar, né? No início nós estamos utilizando como referência básica, né, a RP da DNVGL A204, né, que é para qualificação, né, de Digital Twin, de tecnologia de Digital Twin. É a referência básica, né, que nós estamos utilizando para delinear esse processo. Depois nós vou mostrar basicamente qual o contexto, né, de dutos rígidos submarinos, como aplicar, como nós estamos vislumbrando, né, pensando em fazer essa aplicação do Digital Twin e alguns próximos passos aí que nós estamos pensando também, tá? Bom, como eu disse, né, inicialmente, né, o Digital Twin nós estamos utilizando a norma a Recommended Practice da DNV A204 como nosso guideline básico, né? E a primeira coisa que a gente, só para nivelar um pouco a informação, né, é a definição de um Digital Twin, né, que é uma representação virtual, né, de um sistema ativo, né, onde a ideia é que a gente vai avaliar diferentes estados através de modelos integrados. Essa integração geralmente precisa de um tempo real, que a gente pode considerar, dependendo do modo de falha, um tempo adequado, né? Aqui nós podemos entender como o tempo real, como o tempo adequado de resposta, né, ao longo da vida operacional do ativo que a gente está pensando especificamente aplicar o Digital Twin. Assim, ainda seguindo, né, a estrutura da DNV, né, a gente tentou entender a parte de inputs, né, as entradas de dados, né, os dados em tempo reais, a documentação, tipo de dados históricos necessários para o caso de duto rígido submarino. Deixa eu só botar aqui o ponteiro, aqui só um minuto. A parte de análise, né, quais os modelos computacionais que nós teríamos disponíveis ou os que a gente precisaria desenvolver, né, para a aplicação do Digital Twin, e a parte de output, né, a parte de dashboard, sistemas decisórios, a parte de visualização, alarmes e interação com o usuário que fossem necessários para que, no caso da Petrobras, o Digital Twin fosse aplicável adequadamente. Então, assim, o básico do Digital Twin, onde a RP da DNV nos ajudou muito, foi entender o conceito básico de um Digital Twin, que seria o elemento funcional, né, o functional element. A ideia é que o elemento funcional, ele é a parte, né, o módulo Digital Twin, onde o objetivo básico do elemento funcional é suportar a decisão. Esse elemento funcional, ele é composto de alguns elementos, né, que são importantes, que precisam ter um entendimento completo da estrutura organizacional, né, um dashboard, indicadores de qualidade dos dados que estão sendo aquisitados, né, os modelos computacionais, informações do ativo que são necessários, né, a parte de dados em tempos reais e, muito importante também, como isso tudo vai se inserir dentro da estrutura organizacional da empresa em termos de um sistema de gestão de integridade, né? Aqui, basicamente, o que está escrito aqui, né? O fluxo de informação que já foi descrito anteriormente, só para a gente ter uma ideia, né? Do fluxo de informações e dados e modelos até chegar ao elemento básico, que seria o elemento funcional. Então, a RP ela ajudou muito a gente nessa sistematização de como montar, né, esse processo do Digital Twin, que ele não é um processo isolado, é um processo acoplado a uma série de elementos e requisitos para que se faça essa sistemática adequadamente, tá? E um ponto muito importante, né, que a RP também trata e que é aonde nós gostaríamos de chegar na fase atual do Digital Twin e quais seriam os futuros que a gente pretenderia, né? Então, assim, hoje, né, nós temos uma série de ferramentas que a gente poderia considerar desacopladas ou standalone, porque elas não são conectadas à base de dados em tempos reais, né? Então, um elemento seria o nível zero, né, desconectado. A gente teria também, né, outras etapas, outros níveis do Digital Twin descritivo, né, onde a gente já tem, né, conexões com sistemas de dados e modelos que conseguem descrever os estados, né, dos modos de falha e das decisões que eu gostaria de tomar, né, a parte de diagnóstico, né, a parte e partes mais avançadas que seriam preditivas, prescritivas e autônomas. Só para a gente ter uma ideia, né, fazendo um comparativo, né, com a indústria automobilística, né, hoje a indústria automobilística, né, ela está muito limitada a um nível 2, né, de digamos assim, uma inteligência artificial embarcada no automóvel, né. Não que ela não tenha capacidade hoje de avançar, mas existem aspectos legais envolvidos, né, quando eu dou muita autonomia na tomada de decisão, onde os aspectos legais, um acidente de carro, eventualmente uma morte de um pedestre, algo que tem uma consequência humana ou econômica mais séria, né? Então, hoje em dia, a indústria automobilística está muito limitada até o nível 2, e existem discussões para que ela consiga avançar, não só a tecnologia, mas questões éticas e legais envolvidas, né, para que haja um avanço. Então, a indústria automobilística ela também pode ser um benchmark muito importante, né, para a gente na nossa área de óleo e gás, né, porque dependendo do nível de autonomia que eu desejo chegar, a gente vai ter que considerar padrões, sistemas de integridade e aspectos legais e éticos, inclusive, envolvidos nos níveis mais avançados, onde eu gostaria de botar partes mais autônomas, tá? Então, assim, aplicando na parte do outro rígido, a gente pensou muito qual o contexto que eu gostaria dessa aplicação, né? Quais são os tipos de modelos que eu tenho disponíveis, os modos de falha, como eu vou fazer esse acoplamento, quais os cenários de aplicação, que nós na Petrobras temos dutos de coleta, né, e trunk lines, as linhas, os gasodutos de exportação. Como tratar, se seria possível tratar em novos projetos e campos maduros. Na parte de ver quais as tecnologias relativas ao monitoramento e inspeção que são disponíveis, tá? E na parte da estrutura organizacional, a maturidade com a nossa estrutura organizacional dentro da Petrobras seria capaz de absorver uma tecnologia tão complexa e inovadora, tá? Então, dentro do contexto do escopo, os elementos que a gente foi vislumbrando para desenvolver a tecnologia, a proposta da tecnologia. Só para a gente ter uma ideia, né, um contexto importante entre riser e pipeline, né? A maioria da literatura que a gente vê hoje em dia disponível é muito na área de riser, né? O que acontece com o riser, né? O riser é uma estrutura muito parametrizável em relação ao pipeline, né? O caso, principalmente em dutos de coleta, a gente sabe que o duto ele é pouco parametrizável em termos de gerar, né, essas decisões assim de modelagem numérica muito time consuming, gasta muito tempo, né? Então, por quê? Porque o duto ele é muito dependente, né, da geometria, né, do piso marinho, ele depende muito da interação solo-duto, ele depende muito da interação com equipamentos e crossings ao longo da rota, e depende também de um monitoramento submarino em múltiplos pontos. Então, assim, em relação ao riser, o duto ele tem algumas dificuldades adicionais para que seja feita essa parametrização e acoplamento, e isso a gente tentou considerar nesse nosso desenvolvimento também, que a gente viu que era uma dificuldade adicional, né? Então, só para mostrar aqui, só um minutinho, eu estou tentando tirar aqui agora facilitou a minha vida. O nosso Digital Twin, quais os modos de falha que a gente pensou, né, para o nosso caso específico, tá? No topo eu tenho o nível 0 de representação do Digital Twin. E o que nós queríamos a nível de capacidade decisória, a parte de extensão de vida e inspeção baseada em risco, né, Risk-Based Design, Risk-Based Inspection, perdão. E quais os modos de falha, né, que a gente estaria pensando, né, as ameaças dos modos de falha que nós estaríamos pensando em acoplar, né, a parte de perda de espessura, né, local buckling, fadiga e deslocamentos excessivos, que são os riscos mais eminentes no caso de dutos rígidos, né. E aqui quais seriam os riscos associados. Então a gente abriu essa árvore evolutiva, né, para tentar ver os modelos, né, que a gente iria mapear, né, parte de corrosão interna, externa, global buckling, VIV, slug, né, e pipeline walking. Todos esses elementos eles foram mapeados, né, para que nós pudéssemos desenvolver a tecnologia que a gente está aqui discutindo. A gente também fez uma matriz de risco de maturidade, tá? Onde a ideia básica, né, foi ver, dentro do que nós temos hoje em dia em desenvolvimento na Petrobras, o que a gente precisaria desenvolver. Tentamos responder uma série de perguntas, né, para cada modo de falha desse que nós trouxemos aqui no que eu trouxe no slide anterior. O que a gente observou é que a gente tinha uma série de ações, né, relativa ao Digital Twin, que seria o desacoplado, standalone, e o descritivo, né, como uma série de sistemas, né, que aquisitam dados como pressão e temperatura em tempo real, densidade na Petrobras, mas que para que nós evoluíssemos, né, para áreas relativas a diagnósticos e predição, a gente ainda precisaria desenvolver muita coisa, principalmente pensando na modelagem numérica, em como parametrizar e acoplar, né, a sistemas de coleta de dados em tempo real. E aqui dá para ver também que a gente, a parte ainda mais sofisticada, né, que seria prescritivo e autônomo, a gente acredita que a gente estaria muito distante. A gente tem uma meta, né, dentro do que a gente está prevendo Digital Twin, alguma coisa em torno do chegar num elemento funcional de nível de diagnóstico, talvez, e entre diagnóstico e preditivo no futuro próximo, tá? Basicamente, assim, como é que é feita uma calibração tradicional, né, de um sistema inteligente? Nós temos, assim, os dados que são monitorados, a tecnologia de monitoramento, os dados em tempo real, isso pode alimentar um modelo numérico, e a partir de dados monitorados, eu posso fazer aqui um machine learning para tentar fazer esse aprendizado, né, do meu digital twin, para que eu possa evoluir para etapas mais sofisticadas. O problema é que, no nosso caso de dutos submarinos, esse processo ele é muito time consuming, ele é muito pesado e muito complexo por causa da parametrização que é necessária. Ele não é viável com a tecnologia tradicional, fazendo simulação numérica e tentando fazer esses algoritmos de aprendizado. Como é que a gente tentou passar por esse obstáculo da parte de modelagem, né? A gente avaliou as alternativas para calibração, né? Uma primeira alternativa seria tentar ver monitoramento mais inteligência artificial, né? A gente vê que precisa de muita complexidade em algoritmos de busca. A parte de monitoramento, a infraestrutura é muito pesada, né? No nosso caso, considerando aquele escopo que eu falei, né, de dutos maduros e projetos novos, a gente achou que tinha uma baixa viabilidade e maturidade. A outra possibilidade que nós avaliamos foi fazer monitoramento, mas aquela tentativa de calibração por modelos numéricos, a gente também viu que isso era muito time consuming na parte de modelagem, precisaria também de uma infraestrutura de monitoramento muito pesada. E a opção que a gente achou mais viável, né, que a gente está trabalhando em cima, é o conceito de superfície de resposta, tentando parametrizar modelos, né, em torno de superfície de resposta. Essa parametrização ela se dá com inspeções, dados dos meus ativos que eu tenho. Uma calibração secundária a gente poderia também fazer, quando disponível, com dados de monitoramento para enriquecer essa calibração, e a gente montou, né, todo um projeto baseado no conceito de superfície de resposta calibrado com inspeções e, secundariamente, com dados de monitoramento, né, para atender todo esse contexto aí mais complexo do turismo submarino. Aqui, basicamente, eu mostro um layout típico, né, de duto submarino, né. Essas ferramentas, a ideia delas que a gente tem da superfície de resposta, primeiro a gente precisa parametrizar o meu layout do meu duto submarino, diferentemente do riser, que eu falei que ele é mais parametrizável. Primeiro eu preciso parametrizar o duto em segmentos, né, em comprimentos de VAS, por exemplo, Virtual Anchor Space, e posteriormente essa parametrização ela vai entrar no conceito de superfície de resposta. Então, qual que foi a ideia, né? Nós temos aqui o layout, a gente tem uma série de ferramentas especialistas em desenvolvimento atualmente na Petrobras. Essas ferramentas elas vão receber dados de surveys e dados do meu ativo, né? Elas têm algoritmos especiais que elas tratam esses dados. Elas vão entrar, né, no processo de calibração com superfície de respostas que vão ser disponibilizadas, às vezes, APIs, né, APIs de Internet Applications, e essa calibração vai ocorrer nesse nível. Os dados em tempo reais básicos que nós vamos trabalhar seriam dados de pressão, temperatura, né, que virão dos nossos monitoramentos, e isso geraria a minha ferramenta digital Twin baseada nesse conceito de superfície de resposta, mais calibração por inspeções. Aonde for disponível, a gente vai acoplar também, né, dados monitorados. A questão do nosso dado monitorado que é complicado, porque no duto registro marino a primeira tecnologia e aonde colocar esse monitoramento já é um desafio em si. Então a gente tentou usar o monitoramento em tempo real de outputs como um plus a mais, né, um adicional na tecnologia, tá? Que ela não fosse um pré-requisito para o desenvolvimento inicial da tecnologia, por causa dessa barreira que a gente está aqui conversando. E só para a gente ter uma ideia, né?
Wrap up, please, Carlos, so we have time for the next presenter.
Okay, only more 2 minutes. Only 2 minutes. Only 2 slides to close the presentation. Então, assim, os dados típicos, né, de inspeções que a gente trata são dados de pressão, temperatura e densidade, né? Aquisição de geometria do meu duto, batimetria do piso marinho, enterramentos, e essas ferramentas especialistas, elas transformam isso em tensões, análise de comprimentos de vãos e calibração de frequências naturais. Ela recalibra coeficientes de atritos e avalia os comprimentos de VAS, Virtual Anchor Space do duto, né? Outros dados de inspeções também típicos seriam dados de corrosão e posicionamento desses defeitos. Então, todos esses dados das inspeções, eles vão ser considerados nessas ferramentas especialistas, e associada ao conceito de superfície de respostas, que são outros projetos que nós estamos desenvolvendo para a montagem dessas superfícies de resposta, ele vai fazer uma calibração primária, tá? É o básico, né? Então, quais seriam os próximos passos que a gente está prevendo? A gente observou nesse projeto, no projeto que a gente está aí detalhando e iniciando, né? Que é uma fronteira tecnológica, tá? Envolve uma complexa integração da estrutura organizacional, né, da empresa, para que ele seja realmente útil, né, dentro do sistema, processo de gerenciamento da integridade. A parte de modelagem computacional também precisa de muito trabalho, principalmente nessa montagem de superfície de respostas para os modos de falha que a gente está pretendendo lidar, tá? A gente precisa realmente olhar o que a indústria está fazendo. Então, essa RP da DNV que saiu, a 204, que saiu recentemente, relativamente recente, uns 2 anos atrás, ela nos ajudou muito, né, no conceito, né, de montar conceitualmente as etapas para um Digital Twin aplicado ao nosso cenário Petrobras. E a gente vislumbra ganhos muito relevantes em OPEX, né, principalmente para requalificação de envelopes operacionais, de pressão, temperatura, por exemplo, e para que a gente possa, principalmente em ativos maduros, a parte de extensão de vida, né, que a ideia do nosso Digital Twin é que ele não seja totalmente dependente de monitoramento, porque nós temos ativos já maduros que a gente tem um histórico de inspeções muito grande e isso pode entrar no nosso processo de calibração, tá? E também reduzir a parte de intervenções submarinas futuras e inspeções, tá? Era isso que eu tinha que falar aqui, agradeço muito, tá, para vocês. Tom, sorry for the time that sorry for the delay in the presentation, okay?
Thank you, Carlos.
Thank you, everyone.
Again, we'll have questions at the end. We'll extend this session about an additional 10 minutes. And so instead of ending 15 minutes from now, we will end about 25 minutes from now. We'll now turn to Christian Navoso. I gave a brief introduction to Christian before. He will talk with us about the flatfish technology. So Christian, the floor is yours.
Thank you. Let me share the screen. Okay, seems it's working now. Good morning, everybody. Thank you for being here today. What I'm going to present today is an advanced approach for autonomous pipeline inspection. That is the flatfish AOV that Saipem is developing during the last few years. But let's start talking about why these new technology are needed for the world of the oil and gas. During the last few years, the world of oil and gas changed a bit with the new requirements in demanding of operation, get more autonomous robots in order to avoid to have too many persons working offshore, so reducing the risk of the offshore operation, reducing even the cost of the CAPEX and OPEX, and of course, trying to add some more data and some more inspection frequency on these IMR plants that typically are performed by vessel and ROV, and so are typically very expensive. And we want to change the way of approaching to this kind of services. Even the complexity of the field require for new approach for these kind of activities. The response of Saipem was basically to develop a new concept of subsea robots that are able to perform remote and safe subsea intervention, reduce the carbon footprint since they are not needed to have a vessel following the operation all the time. In this way, you have even a cost-effective results. And you also have the possibility to have more accurate and frequent data collection, even because these new kind of subsea robots are designed for stay underwater, so installed in a subsea field, resident for a few months without intervention with an external support vessel or any maintenance activities. This is probably the game changer for the next few years of this kind of inspection activities. This new family of robots that Saipem developed is called the Idrom Platform. This platform is based on three main subsea robots. These are common innovative vehicle sharing same technologies and are designed to enable a vessel-free subsea intervention. The first vehicle that has been developed was the Idrom R, that is an underwater intervention drone with ROV and AUV capabilities. This has been completed in 2019, and it has been already assigned the first worldwide UED contract. Is going to work on a field in Norway. The second one that has been developed was instead the Flatfish. That is an underwater inspection drone that is more an AUV, an advanced AUV with artificial intelligence capabilities. We will enter more in detail about this after. And the third vehicle is instead the Idrom W, that is more an world-class ROV, full electric, even with resident capability. All these three vehicles have the characteristic to share the same technologies. So in order to have an optimization of the exchange of the capability from one to another, here in terms of technologies and in terms of external tools and infrastructure. In fact, all those vehicles are sensor embedded, but you can even use external tools through interchangeable skid, so adding a functionality that is not always embedded in the vehicle, for example. Or they can even share the subsea structure that allow the vehicle to stay underwater, because you can imagine that as soon as you have the vehicle underwater, you need to recharge the batteries, so you need a subsea base, and that are shared between the vehicles too, and even the management, the data management that allow us to then have the result of the inspection, because all these three tools are used for collecting data, but at the end, what you want to have and what you will provide to the client are mainly an integrated management system in which you can collect all the inspection data that you had collected in your inspection. So going a bit more in detail on the Flatfish. The Flatfish SO is an advanced autonomous underwater vehicle. It's designed for working up to 3,000 meter water depth. It's differently from the typical AUV. It can work more on complex inspection. So typically the AUV used to navigate for inspect pipeline only, but this can even hover close to a subsea structure, or can even navigate in a vertical way for providing vertical inspection of riser or mooring line, for example. It can cover an area more than 100 kilometers with it embedded autonomy. It's battery fitted and can be used as an AUV or a semi-autonomous ROV operation, using, for example, a commanding through optical link or acoustic link. It can be used both in subsea resident application or in surface resident application. We will enter more in detail after. There is a set of a sensor embedded on the vehicle that allow the vehicle to have acoustic visual inspection of the structure of pipeline, contactless cathodic protection survey, leakage detection, environmental monitoring survey, data harvesting, 3D visual reconstruction, riser removal line inspection. The vehicle can be used in two main configurations. The first one, the one that is actually conceived, is the subsea resident. This means that you can deploy the vehicle underwater in the field in which you want to inspect all the structure with this subsea base. The subsea base allows the vehicle to recharge its battery and exchange data with the surface. So this subsea base is connected through an umbilical or through an existing connection to the FPSO or any other subsea infrastructure, for then allow the vehicle to get the power for recharge the battery and for download the data acquired by the inspections. Another way to use the vehicle is instead launching from the surface. It can be from an FPSO, for example, through the flying garage. That is a garage that is not permanently installed underwater, but can be used for launching the vehicle. Then the garage remains suspended while the vehicle can autonomously get out from the garage, start its mission, collect all the information, and then come back to the flying garage for download the data and recharge its batteries. This is a more flexible way to use instead of the one that is permanently used, in which, for example, you have a permanent use of the Flatfish for a very long period. So in this case, the subsea resident application is probably more efficient. In this case, for all the assets you have, like pipeline, manifold, Christmas tree, and a riser, mooring line, you can have leakage detection, pipeline tracking while it's inspecting the pipeline. You can get information for then in post-processing reconstruct in a 3D model of the structure. And this allow to have a very fine, very precise survey of part of the pipeline, for example, or it can even be used for the structure. Then there is the GBI or CVI of all the structure that are subsea, riser tracking, and cathodic protection. Here I just show you a small video that comes from our simulation environment. All the capabilities embedded in the vehicle has been developed by Saipem and have been tested primarily in a simulation environment, as the one that we are seeing here, for then moving to a real scenario. In this case, for example, the vehicle is performing subsea pipeline inspection, following tracking the pipeline, the horizontal one. In this case, you can choose the distance between the vehicle and the pipeline. So for optimizing, for example, in the visual of the vehicle according to the turbidity, for example, it can track the pipeline up to 50 kilometers for then coming back to its subsea base. In this case, you can even get a camera and laser data for then allowing to get the 3D reconstruction of a piece of pipeline or for the full flow line if it's needed. In this case, as you can imagine, the quality and the accuracy of the inspection increased a lot. Here instead, there is a short video in which the vehicle is performing vertical inspection of a riser and mooring line in this case. While the vehicle is autonomously performing this, you can even recognize special feature along the mooring line, for example, a piece of chain or a buoy in a riser. This capability is very useful for this kind of vehicle because it can save a lot of activities that are performed usually with an ROV. And the Flatfish is the first vehicle that can autonomously inspect a vertical structure. Apart the embedded sensor that are integrated in the vehicle, there is even the possibility to add more capabilities and more functionalities through the payload skid. In this case, for example, has been designed a skid for contactless cathodic protection monitoring. While the vehicle is inspecting a pipeline or a structure, through this skid, it can even get cathodic protection data for then post-process and get the whole picture of cathodic protection status of the structure. This, of course, can be even extended to other kind of capability, just changing the sensor with some other sensor that can be used for other functionalities. Apart the one that I already showed, there is even other capabilities like autonomous subsea inspection of subsea structure, of course, of whatever kind of structure that are in a deep water field. Then there is the capability to autonomously docking and undocking from the base, or the autonomously data harvesting of subsea nodes. So how Flatfish is bringing value to the oil and gas field? Actually, mainly its autonomous capability is going to de-risking the activities because you don't need to have, or you can reduce a lot the use of vessel when you use the Flatfish, because as soon as you install the Flatfish underwater, you don't need to come back there to assist and support the activities for months. Of course, these also introduce an environmental impact reducing, since you don't have the vessel in your whole picture, and even the cost will reduce. Another very important point is that is getting more information and more data of your field, maximizing the response, the readiness and the response in case of any failure. How the Flatfish enter, in fact, in the data life cycle in the project execution. as soon as we define the part of the field or the field that need to be inspected, an analysis will be performed to prepare the mission for the flatfish. The flatfish then is pre-programmed with all the mission that you want to perform for getting all the survey that you need. Each mission can provide more than one inspection. So, for example, you can program the vehicle to leave the garage, follow the pipeline, then get in a manifold, inspect the manifold, then go into the riser, and then come back to download the data to in the garage. All this data acquired are then collected in a database, primarily for prepare the anomalies report. This is during the offshore project execution, but then in the home office homework, you can post-process all the data, charge all this data in a cloud, so allowing the client to get all the picture and all the details of this data. Obviously, this can be done inspection by inspection, day by day, month by month. So these allow a final client to get the history of the inspection, and this also allow to have a more precise and more detailed planning for the next inspection, according to, for example, the anomalies that you acquired during the last inspections. This, in fact, Saben what did in this prospect. He developed a life of field data platform in which all the data are collected since the PCI phases. These include even the geospatial service on GIS, enable data storage from operator, collect all the survey inspection along the life of the field, then enable the flatfish mission planning for the next mission according to the data acquired and to the information acquired on the previous inspection, collect the risk, and allow the definition of the next inspection program. This is very useful. It's a common user-friendly visualization map, and in each structure, in each asset, you can then identify all the history, reporting all the inspection, the previous inspection, and understand which of the assets need to have more attention respect to the others. Where we are with the flatfish now, it has been completed, the development and the fabrication has been completed at the end of the last year. This year, we are actually performing a shallow water test at our base in Trieste. For then moving next year to the first deep water deployment in Brazil in Q2 2022 in collaboration with local operators. Thank you very much for your time.
Thank you, Christian, for an interesting talk about technologies that are coming to the market very soon or now. I would like now to open the floor for questions that we might have. And I do have one question that's been submitted. If you have questions, would you please put them in the chat box, and we'll be able to get to them. So the first question is actually for you, Roland. Congratulations. I believe I missed something and it wasn't clear to me. The purpose of virtual ILI is to use this information for real-time risk management. Is that correct?
Hey, thanks, Tom, and thanks for the question. Well, I'm kind of glad it wasn't clear, because the reality is at the moment, the potential uses of virtual ILI, we don't yet know. There are lots of different possibilities. I think I tried to briefly cover some of them. One of the things that we get increasing inquiries about is as a replacement for inline inspection on pipelines where inline inspection is very difficult. So as an alternative when you cannot easily do an inspection. So it's a replacement maybe for external corrosion direct assessment, that sort of thing. But I feel there are lots of other potential uses. And so it could be as part of a real-time risk management process. So there are lots of different ways of looking at it. And we're just interested in hearing ideas from people to say, well, have you thought about this? How would we do it? What data would we need? What would you need to interact with it? Because it's still an early stage development, really. I mean, we have some good applications, but we're not yet doing internal corrosion. We're not yet doing external damage from third parties. We're not yet doing bending strain. We're not yet doing a virtual inspection like the flatfish inspection. You know, you could potentially do use historical data from external surveys to say, well, what would we expect to find from a pipeline in a particular location on the seabed? Do we expect to see a lot of spans and exposure or movement and upheaval? And if we do, then you say, okay, deploy the flatfish. Let's go and have a look to check it out. So the exact uses are yet to be determined.
Thank you. I have a question on the flatfish. So for you, Carlos, is there any possibility that the subsea drones could damage the subsea pipelines?
It's possible, in my opinion. Basically, for the pipeline inspections, actually use more the ROV technology, multi-beam ROV technology, but the AUV, in my opinion, it could be used too. It's a good technology and very interesting, the flatfish technology to be used. I think the flatfish is a TRL5, the maturity of the technology. It's very interesting, the autonomous for this case to be used in the pipeline assets. I think it's possible.
Please put any additional questions that you have in the chat function. I have a question for you, Christian, with regard to some of the flatfish capabilities. You mentioned that you could program in to follow different paths, like to inspect along the length of a pipeline. Does the system have any learning capabilities such that you could do an inspection, let's say that you couldn't program in advance, and ask the system to repeat that inspection at a later time?
Yes, that is something that we are working on. Obviously, at the beginning, we need to train the vehicle to follow the pipeline, for example, or to inspect in the proper path substructure. But then, as soon as we collect all the data coming from the navigation control system of the vehicle, we can even replicate, if we can even improve for the next mission, what's the best path for inspecting, for example, a subsea structure, or for getting some other point of view of the pipeline inspection, for example. So this is something that the artificial intelligence capability that we are embedding in the control system of the vehicle will be available to do.
Okay. I think we have time for maybe one more question. So I'll pose a question for you, Roland. It was interesting to see the elevated density of features in one section of the pipeline. Can you tell us some of the factors that contributed to the elevated increase in density of features?
Hey, thanks, Tom. Yeah, one of the issues to do with the machine learning models is that you don't actually know which parameters they're using for particular choices. So we can look at that and say, well, as I described at the time, it's a low-lying area, it's near to a river, there's some crossings, maybe there's some changes in soil density. So it seems likely that those are the sorts of parameters that the model is using to highlight and to pick those pipe joints as ones for a higher density of corrosion. But there's also things like age, use, maybe even the operator. So exactly what parameters are causing the model to do that, because it's not a traditional kind of analytical model. We can't actually say exactly what it is has caused those ones to be highlighted, but it does seem to coincide with what a corrosion expert would would guess at or would look at and say, yes, that makes sense. The really interesting cases are also when the model is predicting higher density of corrosion, and it's really not clear why. But we also see that in the real inspection data when we come to look at it, and that's showing that the model can just see things that experts, if you like, can't. And that's a repeated pattern that we see across the sort of machine learning and the artificial intelligence business, that these models can actually get better than the humans. But you have to be a bit cautious with that, of course, as to where you're going and whether you really trust them. But so far, it seems pretty good.
Great. I'd like to thank all of the speakers, Roland, Carlos, and Christian, for the interesting presentations and discussion. And that will draw this session to a close. So thank you all for attending, and we'll look forward to seeing you at future events. Goodbye now.